Welcome to the video on phase transitions. Alright, first let's look at some phase diagrams. So we're going to look at some phase changes from a thermodynamic perspective. Now the phase changes include vaporization, melting, which is also called fusion. That's from the Greek word for fusion. Note that nuclear fusion means something coming together, two nuclei coming together. But the Greek word for fusion means to melt something together. So the nuclear fusion means the coming together part. The melting fusion means the melting part. And also the conversion of graphite to diamond is also a phase change, even though it's from a solid phase of carbon to another solid phase of carbon. It's two different phases of carbon. So one way of representing these phase changes, or these changes of state, is via a phase diagram. And so we have one phase diagram over here where we plot pressure versus temperature, and we've got some different lines. So you probably have seen some of these before. We've got the critical point, the triple point. We've got an area here that is solid. We've got an area there that's liquid. We've got an area down here that is vapor or the gas phase. And then on the lines represent equilibria between the two phases on either side. So this line represents the solid-liquid equilibrium line. This line represents the solid-vapor equilibrium line, so that's the sublimation line. This line is the melting curve. And this curve is the equilibrium between liquid and gas phase, so that's the vaporization curve. Know that there's one point, the triple point, where all three phases can come together. We'll look into these some more in the future. Alright, so what is a phase? A phase is a form of matter that is uniform throughout in chemical composition and physical state. So this is something like the liquid phase of water, or the gas phase of water, or a solution, perhaps. It's all the same in chemical composition. So if you look at one portion of a sample and you look at another portion of the same sample, they'll look the same in chemical composition and physical state. An allotrope is a particular form of an element, and it may be solid, liquid, or gas. So diamond is one allotrope of carbon, and graphite is another allotrope of carbon. Also, oxygen O2 and ozone O3 are also allotropes, as are the white and black phosphorus. So now let's talk a little bit about polymorph. So a polymorph is one of a number of solid phases of an element or compound. So this is aragonite and calcite, which are polymorphs of calcium carbonate. So the number of phases can be denoted P, where for a gas or a mixture of gases, that's just a single phase with P equals 1. If we have a crystal of a substance, like sodium chloride, let's say, that's just a single phase. So ice, even if it's broken into multiple crystals of ice, or ice cubes maybe, that's still just a single phase of ice, unless we also have some water around, let's say. So if we have a mixture of two fully miscible liquids in a solution, or rather that is a solution, and that would thus be a single phase. A solution is just one phase because it always is in the same sort of state. If we have a mixture of liquid and solid phases, as in ice and water, of the same substance, then the number of phases there is 2. If we have a mixture of liquid and solid phases of two different substances, as long as the liquid is all of one substance and the solid is all of a different substance, then it's still just two phases. If we have liquid and solid of both substances, then we would have 4 different phases, if the liquids are immiscible. Right, so a system in which calcium carbonate is decomposed, like this, so we have calcium carbonate solid, reacting to form calcium oxide solid, plus carbon dioxide gas. this has two solid phases, the calcium carbonate and the calcium oxide, and one gas phase, the carbon dioxide, and therefore we have three different phases present. The two solid phases plus one gas phase. And let's say if we have two metals that are immiscible, then they'll form a two-phase system. Otherwise, they form an alloy where P is equal to 1. So this is like if we have, if we mix two different metals, if they mix together to form a solution, solid solution, then it would be an alloy. Otherwise, we'll have two different phases. And now the phases may be coexisting at very, very small scales. So they may be mixed together. We may not see a difference on the macro scale, but on the micro scale, if there are two different phases, we still have two different phases present in the system. So a dispersion differs from a solution in that a dispersion is uniform on a macroscopic scale, but not uniform on the micro scale. So here we have an example of a solution. If we look at any one place in the solution, whether on the macro scale or the micro scale, it looks the same. Now that's not to say that all the molecules in there are the same, but if we take a small sampling, if we zoom in on the molecular level, let's say, of, say, sodium chloride in water, one portion of the solution looks exactly the same as another portion of the solution, provided it's been mixed. Which differs from a dispersion, which consists of grains or droplets of one substance in a matrix of the other. So if we look at a dispersion like this, we've got some lighter colored areas and some darker colored areas. So this may be in two liquid phases in a solution, or maybe it's two solid phases in solid metals, let's say, that aren't fully miscible in each other. So we have two different phases. So in the darker areas, we have more of a certain element or compound maybe, and in the lighter areas, we have more of a different compound or element, or they might even just be two different structures where the local structure in one phase is different than the local structure in another phase. So, if we look at a dispersion, a small sample from one of the two phases, or mostly from one of the two phases, might not be representative, truly representative of the composition of the whole thing. And if we look at our dispersion, if we get a portion of our dispersion that's this is mostly coming from this dark spot here, just a little bit from the lighter spot, and so the ratio between the components there is not going to be indicative, or not necessarily indicative, of the ratio in the whole. Whereas if we pick any random part of our solution, we should have a representative sampling of the components that we have in our solution. So dispersions are important in many materials, including things like steels, because they allow us to tune the properties of the whole steel or the whole dispersion based on the individual properties of the individual phases present. So for steels, this is important because we may want a steel that is a little more brittle but stronger, or a steel that is a little bit weaker but is able to flex more, depending on what we want. So maybe we want a bridge that will be able to withstand an earthquake. We want the steel to be able to bend a little bit more without breaking. So we can tune the properties of steels and other materials using dispersions where we have two different phases and we can tune one of the phases, let's say. So now let's look at a phase transition. So this is a spontaneous conversion of one phase into another phase. So this might be phase transitions occur at specific temperatures and pressures. So over here we have temperature versus time. If we're cooling off our sample, we start out with our liquid, and the temperature drops as we cool the liquid. And then at some point, when we get to the freezing point, then the temperature stops dropping as we remove heat from our sample. And the temperature doesn't change, but now we're changing from one phase into another phase. We're changing from the liquid phase to the solid phase. And then once that change is complete, once that phase transition has gone to completion for all of the sample, now the solid starts cooling again. As we remove energy as heat, the temperature drops in the solid. And note that the heat capacities of the liquid and solid phases aren't necessarily the same. Often they can be quite different for different materials, for different phases rather. So here's an example. At 1 atmosphere, ice is the stable phase of water at temperatures below 273.15 Kelvin. And then liquid water is a stable phase between 273.15 Kelvin and 373.15 Kelvin. And steam is the stable phase at temperatures above 373. So if we're looking at temperatures below 273 Kelvin, then it must be that the Gibbs energy decreases as liquid water changes into ice, but above 273.15 Kelvin, the Gibbs energy must decrease as ice changes into liquid water. Because whichever phase has the lower Gibbs energy, that's the phase that is stable under those conditions. So in this region, at these temperatures, so these are high temperatures, temperatures higher than the transition temperature, in this case the freezing or melting point. At temperatures up here, the Gibbs energy of the liquid is lower than the Gibbs energy for the solid. At temperatures down here in this region, the Gibbs energy for the solid is less than the Gibbs energy for the liquid. And at this one temperature, at the freezing point, right, at that single temperature, that's the temperature at which the Gibbs energy for the liquid is equal to the Gibbs energy for the solid. And so at that temperature and only that temperature will we have, for this pressure, will we have the liquid and the solid phases both existing, because now they can be in equilibrium. There's no spontaneity to melting or freezing. So phase transitions are not always easy to detect, so we use thermal analysis to detect them. So what we do is we add or remove energy from a substance as heat, and then record the temperature as a function of time, just like the graph on the last slide. So if the heat added per unit time is constant, then a phase transition occurs when the temperature doesn't change when we add or remove the heat. So in this case, if we're adding or removing heat at a constant rate versus time, then the temperature should change, and as long as the temperature is changing, then there's no phase transition occurring. But then once the temperature is no longer changing, then we have some sort of phase transition occurring. And for the case of liquid going to solid, it's generally a fairly easy thing to observe. Well, you have a liquid, and then after the transition you have solid, and during the transition, during this time, you're forming more of a solid. But it may be that we're transitioning from, say, diamond to graphite, or from graphite to diamond, or something like that. So we may have phase transitions that aren't the common ones that we think about, the condensation or vaporization or sublimation or deposition or melting or freezing. There are other phase transitions as well between solid phases, let's say. All right, so it's important to note that while the thermodynamics describes which phase is the most stable under certain conditions of temperature and pressure, let's say, it doesn't say anything about the rate at which one phase is converted into another phase, and under those conditions, right? So the rate is the domain of kinetics, which we get to later in the course. So it may be that, say, graphite is more thermodynamically stable. So at standard temperature and pressure, graphite is the most common, is the phase of carbon with the lowest Gibbs energy. But diamond still exists because the transition from diamond to graphite is kinetically limited. It's a very slow process. The reverse process is also very slow. This is why diamond, until rather recently, in the last 50 years or so, we haven't been able to make diamonds. We have to go dig them up out of the ground where they've been, where we've had coal and carbon-containing compounds under very, very high pressures and very, very high temperatures for really, really long periods of time on geological timescales. So the kinetics there are so slow that once we remove them from from those pressures and temperatures, the diamonds keep their form for really long periods of time. Okay, so in such cases like diamond, these thermodynamically unfavorable phases may be sort of locked in as solids because the conversion from one phase to another may require the movement of atoms or molecules, which is really slow at normal temperatures in solids. So for diamond, we need to break the tetrahedral geometry around each of the carbon atoms and form the trigonal planar geometry around the carbon atoms that exists in graphite, in sort of the sheets of aromatic rings. And that process is really kinetically limited. It takes a lot of energy to break those bonds. Even though you get back more energy, the activation energy is just so high that the rate at which it occurs at room temperature is so low. All right, so with these sorts of locked in phases, we call these metastable phases because they're not thermodynamically stable, but that conversion process of that metastable phase to the more thermodynamically stable phase takes such a long time. In other words, the rate is low, that for practical purposes, they're stable. So this is the case for carbon, where graphite is the thermodynamically stable state at standard atmospheric temperature and pressure. It's in ambient temperature and pressure. But diamond also exists because it's in a metastable state, and the conversion is kinetically limited. Okay, so for looking at phase stability, all of our considerations are going to be based on the molar Gibbs energy, GM, G sub m, of a substance. And this quantity ends up being so important that as chemists we give it a special name. We call it chemical potential, and we give it a special symbol, mu. So for a one-component system, the chemical potential is equal to the molar Gibbs energy of that substance. So chemical potential is going to be developed in more detail in the next few chapters. So in chapter 4, we're going to deal with chemical potential as an indicator of changes of physical state for the pure substance. So that chapter 4 is the chapter that we're discussing now. In chapter 5, the next one, chemical potential is used as an indicator of changes of physical state for mixtures. So we're going to move from pure substances to mixtures. And then chapter 6 deals with chemical potential as an indicator of changes with chemical reactions. Right? And so this chemical potential idea is going to be really important. Now remember, the chemical potential is just the Gibbs energy, the molar Gibbs energy for a substance. So if we're looking at a pure substance, it's just the molar Gibbs energy for that one substance. If we're looking at the chemical potential for mixtures, it's going to be a combination of the molar Gibbs energies for the 2 or 3 or however many components we have. For a chemical reaction, we're going to be looking at differences in the molar Gibbs energies for the reactants and the products. Okay, so one consequence of the second law is that's central to our discussion here for phase changes is that at equilibrium, the chemical potential of a substance is the same throughout the sample, regardless of how many phases are present. So if we have a case like this, where we have, say, a gas phase and a liquid phase at equilibrium, so at the transition temperature, we have the same chemical potential exists throughout the sample. Now again, the whole sample needs to be at the same temperature, it needs to be well mixed, so otherwise it's not at equilibrium. But at equilibrium, the chemical potentials of both phases is equal. So let's consider a system in which the chemical potential of a substance is mu1 at one location and it's mu2 at a second location. So when an infinitesimal amount dn, some number of moles, an infinitesimally small number of moles of the substance is moved from one location to the other, from location 1 to 2, let's say, the Gibbs energy of the system changes by minus mu1 dn. So we're removing the chemical potential from this number of moles at location 1. And when we move it to location 2, then the material is removed from location 1, and the chemical potential changes by this value plus mu2 dn, because we're now moving that material, that number of moles, from location 1 to location 2. So it now has whatever the chemical potential is at the second location. And so that means that the overall change is dg, the change in Gibbs energy, is equal to mu2 minus mu1 times dn, the number of the infinitesimally small amount of material that we've moved from one location to the other. And so if the chemical potential at location 1 is higher than for location 2, then the Gibbs energy decreases, and thus the process is spontaneous. On the other hand, if the chemical potential for location 1 is lower than the chemical potential for location 2, then the process is non-spontaneous because Gibbs energy is increasing. So for a system at equilibrium, there has to be no change in the Gibbs energy for either forward or reverse reactions or processes, which can only happen if the change in Gibbs energy is equal to 0, and this only happens if the chemical potentials are equal. So in order for this to be 0, when we move some number of moles, and we're saying that the number of moles here, dn, is not 0. In order for dg to be 0, then the difference between these two values, mu2 and mu1, has to be 0, which means they have to be the same value. Right, so that's phase transitions.